Um, our next speaker is Daniel Groves, and he will be telling us about hyperbolic groups, no, mesoscopic topology, and hyperbolic groups with planar boundary. Take it away.
Thanks. Yeah, thank you to the organizers for organizing this wonderful conference in this wonderful place and giving me the chance to talk. It's a great honor. So I am going to try and tell you about a thing I'm trying to call mesoscopic topology, and how I think it relates to questions about the possible existence of hyperbolic manifolds. So here are some questions and, well, conjectures that I like and like to think about. Oops. So my favorite one is due to Cannon, and it says G is word hyperbolic and the boundary at infinity of G is homeomorphic to the two-sphere, then G is virtually, I'll say Kleinian, but virtually the fundamental group of a closed hyperbolic three-manifold. So this goes back to the early 90s. Cannon was trying to understand group theoretic versions of what was happening in Thurston's geometrization program, and this became part of an approach to geometrization, which wasn't how things went eventually, but this is still open, maybe even wide open. And I like two related conjectures. So the second one, due to Kapovich and Kleiner, and so it asks about those hyperbolic groups with a different kind of boundary, the Sierpinski carpet. So G is word hyperbolic. And boundary G, I'm just going to say, is a carpet, so a Sierpinski carpet. And again, that's just homeomorphic to, then G is virtually Kleinian. So now it should be the fundamental group of compact hyperbolic three-manifold with higher genus boundary. And so you could realize it with totally geodesic boundary if you like. And then the peripheral circles in the Sierpinski carpet correspond to the limit sets of the boundary subgroups. And then there's a third conjecture that I like as well. So it's not due to, I like to call it relative canon. It's not due to the person relative canon. I learned of this from Kapovich. And so now, maybe now I have an extra subgroup. So this is relatively hyperbolic, and I'll tell you a bit about that. And P is a subgroup of G, which is a z-squared subgroup. And relatively hyperbolic groups also have a boundary at infinity. And if that's a two-sphere, then G is virtually Kleinian. So this corresponds to the finite volume hyperbolic case. P should correspond to the cusp subgroup. So a word hyperbolic group is just a group that acts properly discontinuously and co-compactly on some delta hyperbolic space. So coarse negative curvature, but you don't insist that that space has any other extra geometry than being a geodesic metric space whose triangles are slim. So a relatively hyperbolic group is a group that acts properly discontinuously on a delta hyperbolic space, but not any longer co-compactly, just in a geometrically finite way. So there's some collection of horoballs that are preserved by the group action, and the quotient, in this case, there's a single parabolic, and the quotient is quasi-asymmetric to a ray. It looks like a compact piece and a cusp coming off. But that comes from the quotient of a horoball. And we might see a little more about what that means. So these are coarse versions of things to do with the actions of hyperbolic, fundamental groups of hyperbolic manifolds on HN. And so answering these questions is really, is there a hyperbolic manifold? Okay, so I'm not going to answer any of these questions today. So here are some things that are known. So maybe I'll call these conjectures 1 and 2 and 3. So in the same paper that Kapovich and Kleiner formulated this conjecture, they proved that the Cannon conjecture implies their conjecture. So they have this hyperbolic group. They identified from the fact, so they have the carpet, the Sierpinski carpet, as the boundary at infinity, and they actually said, oh, well, just from those peripheral circles that we can see in the carpet, we can find some subgroups of G that are virtually surface groups, that are peripheral in some sense. And then they said, we'll take a graph of groups where we just double the group G along those surface subgroups. We glue them together, and they said, oh, great. That gives us a bigger group in which G embeds, which has a two-sphere boundary. And you can sort of see that two-sphere is coming from gluing together a whole bunch of Sierpinski carpets nested in. Each time you see a peripheral circle, you glue in a Sierpinski carpet, and then you keep doing that forever, and then compactify with the boundary of the Basset tree, corresponding to this splitting. And so then that doubled group should be virtually Kleinian, according to Cannon, and then therefore this would be a subgroup of a Kleinian group. Okay. Oh, I forgot to mention. So everything, well, not everything, but the main things that I'll talk about today are joint work with Peter Heisinski and Jason Manning and Damien Asada and Alex Sisto and Genevieve Walsh. And I'm going to use these initials. So a subset of the authors, it was the, I guess, odd-numbered authors, because I'm the first one. So Groves, Manning, Sisto. We proved in about 2019, I think that's when it was published, that 1 implies 3. So if you knew the Cannon conjecture were true, then you can deduce this relative version of the Cannon conjecture. There are other conjectures that are related to this. You can think about hyperbolic groups whose boundary is a subset of the sphere but isn't this particular one or this one, and other relatively hyperbolic groups as well. But these are the 3 that I want to focus on today. And if you're trying to prove this one, what we did was say, oh, just like in the case of a finite volume hyperbolic 3-manifold, where you can do Dane filling, and Thurston says you'll often get a closed hyperbolic 3-manifold. There's a relatively hyperbolic version of Dane filling, which is we should take this peripheral Z cross Z. If we're going to glue a solid torus onto that torus, we quotient Z squared to get Z in some way. You just do that group theoretically, and you get a quotient group of G. And we proved that often that quotient group can be made to be a hyperbolic group with two-sphere boundary. It's then not quite so obvious how to use the Cannon conjecture, and we said actually there are infinitely many quotients of this G that are hyperbolic groups with two-sphere boundary, and those quotients are injective on larger and larger finite sets. And so we said, okay, well, if each of those quotient groups happens to be virtually Kleinian, then we can sort of use the just use discrete faithful representations. Those limit to so discrete faithful representations of the quotient give us discrete non-faithful representations of this group, but their limiting representation is faithful. So anyway, okay, so that's how we proved that 3 implies 1. Now, neither of these are in the right order. You'd really like to go the other way. Why? The Cannon conjecture is the most important of these conjectures and the most mysterious. And conjectures 2 and 3 actually should be easier. You shouldn't be using this conjecture to prove these. These should be easier. And why is that? The expected manifolds here have non-empty boundary. the finite volume case, and I'm insisting that there is a P here, so this is finite volume and non-compact, and there's a compact manifold with torus boundary or with higher genus boundary. So they have non-empty boundary, and so they're Harkin 3 manifolds. And Harkin 3 manifolds are much easier to understand than arbitrary 3 manifolds. And for example, geometrization was known decades earlier for Harkin 3 manifolds, using techniques that are much more geometric group theory friendly than Perelman's Ricci flow. So these conjectures should be easier, and they're less important. So you should prove these first, and then hopefully use that to work on the Cannon conjecture. And so I want to talk about a first step towards that today, and sort of a couple of the ideas behind how we do that, which hopefully will have more applications. So here's an application of the main theorem. The main theorem's a little more technical, and we'll get to it. So this is now all of us. Sorry, don't forget Peter. GHMOSW. And it says if 3 holds, doesn't quite say then the Cannon conjecture is true. I'd love to prove that, but I don't know how to prove that. But it says it under a hypothesis. So and G is residually finite. Hyperbolic with 2-sphere boundary. Then G is virtually Kleinian. So we've seen residual finiteness, and obviously fundamental groups of actual hyperbolic manifolds are residually finite because they're linear, but we don't know actually whether all word hyperbolic groups are residually finite. That's an open question. According to these conjectures, all of these groups with these sorts of boundaries should be residually finite because they're supposed to be virtually Kleinian. But that's not known either. So if you assume residual finiteness, then we can deduce the Cannon conjecture from the relative Cannon conjecture. And as I tried to indicate, that should in some sense be easier. Relatively hyperbolic groups are not easier than hyperbolic groups, but at least here you have a boundary. And there are various reasons to think that that actually could be useful in a way that you don't have here. Okay, so that's sort of where I want to aim towards today. Pardon? Yeah, the intersection of all of the finite index subgroups is the trivial group. Okay, and in particular, what that says is that there are lots of finite index subgroups. Maybe there are none without an assumption of that. It's possible there are non-elementary hyperbolic groups which would have no finite index subgroups at all. But so the mesoscopic topology is related to why I think having residually finite is a really useful hypothesis in this setting. This is just a group. We don't have a nice space upon which it acts. Maybe it acts on the Cayley graph, or there's a nice contractible space on which it acts, the Rips complex and so on, but we don't have a manifold. If you make a group act on its Cayley graph, the quotient of the Cayley graph is just a rose. There's one vertex and a bunch of edges. And that's got no nice structure at all. On the other hand, there are nice large-scale structures to delta hyperbolic spaces, and I'll talk about a few of those today. And what residually finite allows you to do is say, if I fix a specific scale in advance, then balls of that size in my model space for G embed in the quotient by some finite index subgroup. So residually finite allows you to make a very large injectivity radius assumption on your space to be able to see some more structure. And so finding that fixed large, but because it's fixed medium scale, and then hoping to do topology at that medium scale is why I call this idea mesoscopic topology. I know of the word mesoscopic from a paper of Gromov and Delzant on mesoscopic curvature. This is totally different, but it just means medium scale. It's between microscopic and macroscopic. Okay, so residually finite that's what that means, and that's why it's useful. You can make a large injectivity radius assumption for a compact quotient by some finite index subgroup of whatever your model space is, and maybe in this case it's just a Cayley graph. Okay, so that's sort of the big idea about assume things are residually finite and then try to do geometric topology on graphs or cell complexes or whatever using the large-scale structure that you get from assumptions about the boundary being this nice thing and what that means for the delta hyperbolic space that's inside the boundary. Okay, and this project with the 6 of us is the first sort of instance of this program. And that's the main big idea, and the big idea for this paper is to implement that idea for drilling. We have a closed manifold, try and approach. We have this thing that's supposed to correspond to a closed manifold to try and approach the Cannon conjecture. And one thing you can do with a closed 3 manifold is take a geodesic and remove it, drill it out. And get a manifold with boundary. And that's sort of, we're going to do that in a group theoretic context. So group theoretic drilling. So that's the main tool to get to the main theorem for proving this theorem. Okay, great. So let me give you the definition of group theoretic drilling. Okay, so we're going to do it just in the context of hyperbolic groups. So G is a word hyperbolic group. And I have some element. You should think of this element as the element of the fundamental group that up to conjugacy represents your closed geodesic in your space. And so it should be a primitive geodesic. So this should be maximal cyclic. I'm going to ignore all issues of torsion today. Drilling of G along G. So it's a group. So it's actually a pair of groups, a group and a subgroup. So a relatively hyperbolic pair, G hat and P. And a normal subgroup of P. So G is, I'm going to write the definition, then I'll talk a little bit about what on earth is going on with this definition. So G, the original group, is realized as a quotient of this mystery group G hat, and it's the quotient by the normal subgroup of N, which is the normal closure in G hat of N, which is a normal subgroup of P. So you should think I've built a manifold with torus boundary, where that torus is a regular neighborhood of the geodesic that I drilled out. That P is the fundamental group of the boundary of the regular neighborhood of that geodesic, so you should think that's a Z squared. And N is the subgroup of that generated by the meridian, that's the curve on the torus that bounds a disk in the solid torus that is the regular neighborhood. And that's what that N is. And if you apply Van Kampen to try and calculate the fundamental group of the closed thing from the fundamental group of the thing with boundary plus a solid torus, then you'll see that's exactly what happens when you apply Van Kampen's theorem. The Seifert-Van Kampen theorem. And so the last thing is that this does the correct identification. So we have the quotient map from G hat to G takes the quotient of P mod N to this group element G that we started with. Okay. So that's a group theoretic drilling. And you could say, okay, well, that's a thing that you can write down. Do they ever exist? And the answer is yes. So we give you 3 examples. So example 1 is G is pi 1 of M a closed hyperbolic 3 manifold. G represented by represents simple geodesic gamma, and G hat is the fundamental group of the complement M minus gamma. And then P is the subgroup of G hat that corresponds to the boundary torus that you get, or the for G hat. Okay, so that's what we're motivated by. Here's a second example. G hyperbolic and G with G maximal cyclic. And now I'm just going to define a new group. It's going to be G. And I'm going to glue on a Z squared to G, not as a free product, but as an amalgamated free product. So maybe this is generated by elements A and B, and I'm just going to glue G to A. Okay? So long as G represents a maximal cyclic, a maximal elementary subgroup of capital G, it turns out this is a relatively hyperbolic pair. That follows from a theorem of Domani. So you can do this in total generality. Any group and any reasonable element can be drilled to get this group. So this is kind of stupid. Because you're never going to learn anything about a mystery group G by embedding it as a vertex group in a graph of groups. That's not how these things work. So we call this the trivial drilling, and it's not going to be very useful. So the main theorem is going to be that in the context of a hyperbolic group with two-sphere boundary which is residually finite, some finite index subgroup can be drilled in a non-trivial way. And it's going to be drilled to get a group that fits into this conjecture 3. So it's going to have a two-sphere boundary as well. Okay, and I'll get to that in a minute. I'm not going to write anything up here, but actually there are many other examples of drilling. It doesn't have to be just a 3-dimensional phenomenon. You can non-trivially drill free groups, surface groups, higher dimensional hyperbolic groups. In some sense, it's a converse to this relatively hyperbolic Dane filling that I talked about. This is a Dane filling map. So anytime you have a Dane filling where you took your peripheral group and made it cyclic and got a hyperbolic group, then undoing that is a drilling. So for example, the fibered hyperbolic 5-manifold that Bruno was talking about, in that paper, they take the cusps and crush them down group theoretically to cyclic groups just by doing a group theoretic quotient to get a beautiful word hyperbolic group where the image of the fiber has very beautiful and surprising properties, but in particular is not hyperbolic. So going from that filled thing back to the fibered hyperbolic 5-manifold is a drilling in this sense. So you didn't start with a manifold, but you ended up with a 5-dimensional manifold. And you can do that in any dimension. But where you can really get some control is in dimension 3. Okay, are there any questions? Okay, well, let me tell you the main theorem, and then I'll tell you how the main theorem gives the application, and then I'll tell you some ideas in the theorem. Okay, so here's the main theorem. Okay, so suppose G is residually finite. Word hyperbolic. The boundary of G is a two-sphere. There is a finite index subgroup G0 in G and a drilling G hat P of G0. So P is Z squared. And 2, this boundary of G hat is S2. I didn't tell you what the boundary of a relatively hyperbolic group was, but I almost did, because I told you it comes from an action on a delta hyperbolic space, and it's just the boundary at infinity of that space that I talked about, the one on which there's a geometrically finite action. Okay, so if you look at our paper, we admit the possibility of a Klein bottle here. But actually, there is a finite index subgroup where when you drill, you get a torus. So I'm going to tell you first how to get that theorem, and then I'm going to tell you a little bit about the ideas. And the first thing I'll tell you is how to, one way to, well, 2 ways to see this subgroup here. And in one of them, we'll see why it could be a Klein bottle, but doesn't have to be. Okay? So, let's prove the application of this main theorem from this theorem. So, we're trying to prove that our group G is virtually Kleinian. Well, and it's enough to prove that G0 is virtually Kleinian. G hat is virtually Kleinian by conjecture 3. In particular, it's the fundamental group of a 3-manifold, and the way that, I mean, this P here has to be, you can make it a 3-manifold with boundary where this P is the fundamental group of the boundary torus is a Z squared. Okay, because the virtually Kleinian group has to be finite volume, and this is the only Z squared, and it has to be the cusp subgroup. And now to get G, we saw how to do it group theoretically. You fill in a meridian of a solid torus, group theoretically, but you can realize that group theoretic quotient via gluing a solid torus to the boundary of the 3-manifold that we got from G hat by conjecture 3. And G will just have that as the fundamental group. Okay, so it's actually, so this application is actually easier than the one for 1 implies 3, the end game. Okay, so this is very much the heart of the matter. Okay, so my next thing I'm going to do is talk about some ideas about how to do this drilling. While I erase the board, please feel free to ask any questions. Okay, so ideas. Take 1. Okay, so here's the cartoon sketch of what we would like to do that can actually be made precise. So take X, a Cayley graph of G with axis L for G. So this is just a real line. G acts on it by translations. The quotient is a circle. Find finite. And this G actually is just any element that generates a maximal elementary subgroup. We can drill any element at all. Given the element, there is a finite index subgroup containing it that drills it. We can do any one but a different finite index subgroup for different things that you want to drill. So find finite index G0 containing G with large injectivity radius Okay, we're just in a graph, so what does that mean? The quotient map from x to x mod G0 embeds large balls of x. And how large is, that's what the injectivity radius is. With large injectivity radius, so this circle, axis mod G, has a large, nice, regular neighborhood. T. So large is okay. All of these things should be put in scare quotes. You should think then now that T is just a nice solid torus. And then in X mod G naught. Okay. Yeah, I didn't finish the sentence. Yeah, so X mod G, as I said, is just a rose. X mod G0 is a graph with many vertices, and large balls in this graph look like large balls in X. But it's still compact, and it has this circle contained in it. Okay, so you have to be a little careful. In order to make this precise, G would have to actually have large translation length, but you can do that. Okay, and then what's G hat? Well, it's supposed to be the fundamental group of the complement of the regular neighborhood in this quotient space. I'm just going to put a course here. And then this can be made precise. If you make precise what a coarse fundamental group is and what a nice regular neighborhood is, and so on. Okay, so that really is what you would expect it to be, except that none of these words really make precise sense or would expect to give you what you want. And a lot of the work is how to make these ideas precise. And usually we're working up in X and not in this quotient space. But okay, so take 2. Which might be a little more useful. So G acts on this 2 sphere, the boundary of G. And that's a nice action by homeomorphisms. There are some slightly better metric properties than just homeomorphism, but not much. And you should certainly not think of those metric properties as corresponding to a round sphere, because if this related to, like if it was acting quasi-conformally on the round sphere, then you would be done. You would know you were virtually Kleinian. So it's just some topological 2-sphere and some action by homeomorphisms. And the element G, being loxodromic, has 2 fixed points at infinity. It's repelling and attracting fixed points. Okay, so I can take the subgroup generated by G, and I can quotient, well, it preserves the fixed points, so it preserves the complement of the fixed points. So that's an annulus, and that's a cyclic group acting properly on an annulus, and the quotient is either a torus or a Klein bottle. If you pass to a finite index subgroup of G, index at most 2, you can assume it acts orientation preservingly on the 2-sphere. So just do that, and then this is a torus. So here, P will be the fundamental group of the boundary of this regular neighborhood T, whatever that means. And here, you can see P very explicitly from infinity, but it's very hard now to see what G hat is going to be, because G acts with dense orbits on the sphere. So capital G. Lowercase g acts just as this one north-south dynamics. Capital G acts densely. So seeing what G hat is from this perspective at infinity is much harder. But But this is two different and equally valid ways of seeing what the group P is. So this is P, pi 1. So let's call this C for torus cusp, and then P is going to be pi 1 of C. And we make that very explicit and precise in the paper. Okay, so let's get to the mesoscopic topology. I want to link I want to link these two perspectives, and in doing so, start to identify what I mean by a large fixed scale at which we can do geometric topology. Yeah, so that's take 3. And this is where the mesoscopic topology comes in. Okay, so I'm going to draw the same picture. And then there's an axis, L, going through the middle of the space. So I've got my boundary at infinity. I'm thinking about x as being on the outside of that, as the inside of my boundary at infinity. So my boundary at infinity just comes from equivalence classes of geodesic rays from the base point, where two rays are equivalent if they have bounded Hausdorff distance. And what I'm looking for is to make the space on the inside nice. Okay, so I want to take I have this quasi-geodesic, you should maybe think of as a geodesic, quasi-geodesic L that is preserved by G. G is just acting by translations. And I want to take a large neighborhood of that inside of my hyperbolic space. So that looks like some sort of a banana. So that's like radius R. Okay, so the picture that I drew just makes it look like I have this large infinite annulus as the boundary of this neighborhood of L, and I would like to make that precise. So, so we have given L and a number R. So TRL, that's the tube around L of radius R, is the x in x, so that the distance from x to L is less than or equal to R. And the shell, SRL, is the same thing, but it equals R, the set of points distance exactly R. So I have the tube is the neighborhood, and the shell is the boundary of that neighborhood. Now I'm in a graph. Let's just make R an integer. SRL is just a collection of vertices. Okay, it's a discrete set. So in particular, it's not an infinite annulus. It's just a discrete set of points. Okay, so claims. Sufficiently large R the R shell around my L, maybe I'll drop the L, but well, we'll see, is coarsely connected. So if I join by an edge all of the points in SRL that are at distance at most 8 delta, where delta is my hyperbolicity constant for my Cayley graph. Then I get a connected graph. So it's just a set of points, but it's sort of, it's at least coarsely connected. Okay. And then, okay. The second claim is going to involve a definition. So I can take a point on the boundary, some Xi, and I can take a point, I'm just going to fix a base point, W on L. That's my base point for the boundary. So now the points on the boundary can be seen from, take a geodesic from W and go out to the boundary. And then if two geodesics fellow travel for a long time, then the points on the boundary are close. If they fellow travel forever, you get the same point on the boundary. So I can choose for my Xi a geodesic from Xi, from W, a geodesic ray that starts at W, and a geodesic representative of Xi. And that geodesic, at some point, will get distance r away from L. Unless I have one of these 2 points here, in which case I will travel near to L forever. But if I take any point that isn't one of these 2 points, the geodesic might travel along L for a while, but then eventually it leaves L, and it continues to leave L at linear speed. And eventually it crosses the R, crosses out of the R neighborhood of L, and never returns. So there's the last point in the R neighborhood, and that's of course on the R shell, and that is the projection at scale R of Xi. So I have a projection map, capital Pi sub R, and that goes from the boundary of G minus these 2 points to the shell SRL. Okay. Okay, so the second claim is about this projection. So the projection pi r so it's an isomorphism on fundamental groups from the fundamental group of the boundary minus these 2 points to this thing that I'm calling pi1 course of the shell. So what's pi1 course? Well, I told you how to make it a connected graph by adding in bounded length edges. And now you just take some number, d, and every loop of length at most d in this graph that you made connected from the shell, you glue in a disk, and you take the fundamental group of that space. You can also phrase this in terms of a coarse category, in terms of coarse paths and coarse loops and coarse relations. So you have to identify the scales at which you're doing this coarse fundamental group. How long are the edges that you're adding in? How long are the loops that you're adding in? And part of the claims here are that there are numbers that work, and those numbers are independent of R for sufficiently large R. How to join up the points, that's at scale 8 delta. The loops, that's a more complicated number involving various things. So this is one of the first main technical theorems that we prove, and it says that, so of course, this is just Z. This is just Z, because it's an annulus. And it says that if you take a loop in the sphere that separates G minus infinity from G plus infinity, and you project it down onto this shell, you get an essential loop in this coarse fundamental group of this shell. Okay. And there's also an isomorphism fundamental group of the shell and the fundamental group of the complement of the tube. Okay, so I was thinking just about the fundamental group of this shell, but I could also think about loops that avoid the tube entirely that go a long way away, and those two things are also isomorphic. And that's actually much easier to see. You just use delta hyperbolic geometry to project. Okay. So this uses various analytic properties of the boundary of the group being linearly connected and doubling and so on, and a lot of delta hyperbolic geometry. Okay. All right, how much more do I want to say? Okay, so I'm going to take this space. So remember, this is Z, so this is Z, so this is Z. So take the Z cover, let's say Z of X minus this tube. Okay. So if you were honestly in hyperbolic 3 space, I've removed this hyperbolic tube. For large R, the frontier of this shell looks pretty Euclidean. And then I take an infinite cyclic cover of that to get something that looks like hyperbolic space up here, although there's a Z's worth of hyperbolic 3 space up here. And there's a thing that's close to the plane, which is the universal cover of this annulus here. So that's what that Z cover is. So that's got a coarse plane in it. This contains a coarse plane. I'm going to call this the universal cover, but it's the coarse universal cover of this shell. And I know that that's a coarse plane because there's a Z action on the shell, and there's a Z action coming from that Z cover, and that gives a Z squared or Klein-Bottle action on this S tilde with compact quotient, and so it's quasi-isometric to the plane. And if you glue a horoball onto SL, we get a new hyperbolic space. Let's say Z hat, also delta hyperbolic. Now what happened to the visual boundary of Z hat? Well, a little bit of thought should convince you it's plausible that actually I took this annulus, that's the complement of these 2 points, I took the infinite cyclic cover of that, and I got a plane, and then I compactified that when I added on a horoball with a single point, and so I compactified the plane to S2. So this also has boundary S2. Yeah, there are lots of ways that you could do it. Any graph can be made a horosphere of a horoball. Basically, you're just taking a warped product by some exponentially distorting warped product. There are various subtleties about exactly how we want to do this in this graph, but that's pretty straightforward. Or at least Jason and the others of I have been doing it for 20 years, so it feels straightforward to us. I'm happy to talk to you about it later, but maybe not now. Okay, so Z hat is step 1 in an infinite process. There isn't a geometric group or even a geometrically finite group acting on Z hat. There's just a Z squared coming from this P. So what you do now is you take all of the other translates of the axis L, and the large embedded neighborhood can be translated here to all of these R tubes are disjoint from each other under the G0 action. So under this cover, you have a whole bunch, infinitely many other tubes, and they lift. And you unwrap those and glue on horror balls, and you do this one after the other after the other. At each stage, you get a boundary S2. And in the limit, and there's just a limit of graphs, if you like, you get a space that has an action, and that's a delta hyperbolic space with an action of some group on it, and that group is the G hat that we build. And then we have to mess around to show that the boundary of this limiting space is S2. But it is. I think in the interests of your time and your sanity, I won't say any more than that about the details, and I'll rather just stop and say thanks.